Hannah Rosenberg, founder and director of Velas Commerce, and in this video we're going to walk through blockchain mechanics. And don't worry, no technical knowledge is required to follow along with this video. So the first question you may have is, why do you need to understand blockchain mechanics? And well, you may just be curious, but also if you're in any kind of position where you need to be analyzing different blockchains or different blockchain use cases or different blockchain applications, then understanding what a blockchain is actually doing is going to be hugely helpful to you there. So let's start by looking at the problem that the first blockchain, Bitcoin, was built to solve. And to do that, let's go back in time to the 1980s. This is when the protocols that we all use on the internet today were still being built. So I imagine all of you have ran across error code 404, page not found, right? You type the URL in your browser wrong and you're going to see this error code. But there's another error code out there which was made at the same time and held for future use, which is error code 402, payment required. And you've probably never ran across this one. So I tell you this to give you the perspective that from as early as when the internet was still being built, there were people out there that envisioned and were actively working on digital currencies, right? Cash for the internet. Some of the early projects launched actually in the 80s. There's a well-known project called DigiCash that actually launched in 1989. And there were many other experiments like this as well. But all of these early digital currency projects had one major problem. And we call that the double spend problem. And that's just a fancy way to say, hey, digital goods are really easy to copy, as in copy, paste, easy to copy. And well, this is a big problem when it comes to money, because if you have some, big long string of text that represents a digital coin, well, you have that coin and you're like, hey, wait a second, I can just copy, paste, and now I have 2 coins, and then I have 5 coins, and then I have 1,500 coins. And quite quickly, you can see how this would destroy a monetary system. So all of these digital currency experiments, they solved this problem with a centralized architecture, right? They had one server, one entity, one business that did the job of deciding who had what when. This one server would do the job of saying, hey, Alice, I'm sorry, you've already sent that coin to Bob. You can no longer send that same coin to Charlie, etc. So this double spend problem is the problem of how do you create digital scarcity? How do you decide who has what and when? Now, Bitcoin is what we often call a cryptocurrency, and cryptocurrency gets its name because it relies very heavily on the use of cryptography. And there's some very, very clever cryptography and mathematics that go into these systems, but that cryptography does the job of validating who actually owns a coin or who did indeed sign a transaction. So cryptography will validate a transaction, but it won't order it for you. It won't help you figure out who sent which transaction was sent first, right? It doesn't fix the double spend problem. So this was a big problem until a person or a group of people calling themselves Satoshi Nakamoto invented Bitcoin. Satoshi had a very interesting idea. Satoshi wanted there to be digital currency that wasn't a business or a particular server, but actually existed as genuinely peer-to-peer cash, as a protocol on the internet. So Satoshi had the idea, instead of one central server, central business doing the job of deciding who has what when, the entire network would. Everyone would come to an agreement or a consensus on who has what when. And well, this is a bit of a trick too. How do you get a group of people who don't know and don't trust each other to agree upon data? Well, let's walk through the solution that Satoshi came up with. Okay, let's start by remembering here that what we are talking about is just software. Bitcoin is just a program that you run on your computer. And who's running this? Well, anyone in the world. Anyone with a half-decent computer and an internet connection can download that software and run it and be a part of the Bitcoin network. It's important to note that we also often call these computers on the network nodes. We say it's a node on the network, which just means computer. But again, this is just software. So there's no Bitcoin business, there's no Bitcoin CEO, and very importantly as well, there's no Bitcoin help desk if you get yourself into trouble. But it's very helpful just to keep this picture in your head of this is just software that is being run on people's computer, anyone's computer, anyone in the world. So let's start by walking through the example of an attempted double spend. Let's imagine that we have Charlie. Charlie legitimately owns 1 Bitcoin, but he owes 1 Bitcoin to Alice and he owes 1 Bitcoin to Bob, and he's going to attempt to send both of them the same coin. Now remember that cryptography can do the job of validating that Charlie does indeed own that Bitcoin and that Charlie did indeed sign that transaction to Alice and sign that transaction to Bob, but it can't do the work of deciding who should actually get that coin. This is where we need the blockchain. So let's imagine the blockchain network. We have all of these different computers. These are just people all around the world who don't know each other or necessarily have any reason to trust each other, but all people who have chosen to download the Bitcoin software and run it. So we have all these different computers talking to each other. And then we have Charlie with his 1 Bitcoin, and he's going to broadcast 2 transactions, sending that same coin to Alice and Bob, and he's going to broadcast these transactions at the same time. So let's imagine that one half of the network saw that transaction going to Alice first. And so all the nodes on this side of the network, all the computers on this side of the network, they think Alice is getting that Bitcoin, and this other transaction to Bob, well, that's a double spend, and so we're just going to reject that. But the other half of the network, well, it saw that transaction going to Bob first, and so it thinks that Bob is getting that Bitcoin and this other transaction going to Alice, well, we're just going to reject that as an attempted double spend. So now we have this disagreement on the network. Half the network thinks that Alice should get this Bitcoin, and the other half of the network thinks that Bob should get this Bitcoin. Well, how do we solve this? Well, you may have heard the term miner or mining or consensus algorithm or perhaps proof of work. And all of these terms are referring to the same process here, the process of coming to agreement, the entire network coming to agreement on whether or not Alice or Bob gets that Bitcoin. So let's introduce you to miners. Now, a miner or a mining machine is just a fancy computer. It is a computer that is very specialized. It has specialized computer chips in it that are very, very good at crunching very specific mathematical equations, right? It's a computer special built for this purpose. So these miners are these specially built computers which are really good at crunching these specific numbers. And these mining machines exist because the Bitcoin network sort of sets up this competition between these computers. It sets up this competition where you have to solve this really challenging mathematical puzzle. So let's imagine that I am a miner sitting on the Bitcoin network and I'm watching all this transaction data going back and forth, right? Danielle sends Erica 2 coins, Erica sends Rodrigo 5 coins, etc., on and on. I see all this different transaction data going on. I gather all of this data up into a chunk or a block, right? I have this block of transaction data. Then I'm going to take that transaction data and use it to help solve this mathematical puzzle. And this is really cool because the mathematics involved here are really neat. This is done and set up in such a fashion that it's going to take this mining computer probably about 10 minutes, right, to solve this really difficult mathematical puzzle. And I've got all these computer chips that are just crunching away as fast as they can, and eventually, in about 10 minutes, one of my computers will solve that mathematical puzzle. But the math is done in such a way that once I solve that puzzle, I can take my block of transaction data and the solution to that puzzle, and I can broadcast it out on the network, and all the other computers on the network, all the other nodes on the network, it'll only take them just a fraction of a second to validate that indeed I solved that puzzle, right? I won this round of the mining competition. So let's go back to our Charlie double spending example. We have this conflicting data on different parts of the network. Now, in reality, there are thousands of miners on the Bitcoin network at any given time, but for simplicity here, let's imagine just 2. We have one miner on this half of the network which thinks that Alice is getting that Bitcoin, and we have another miner on this half of the network which thinks that Bob is getting that Bitcoin. Now, there is some luck involved here. Whether or not you can win a mining competition is going to depend primarily on how good your computers are, but there's also a little bit of luck involved here. A computer might happen to come across a solution first. But let's imagine that this miner who thinks Alice is getting that Bitcoin, they win that that race, right? They find a solution to that mathematical puzzle. They take that block of transaction data that includes the transaction to Alice, and along with the solution, they broadcast it to the network. Everyone can see, oh, yep, they won. Okay, I guess Alice is getting that Bitcoin. And then we move along to the next round, and Charlie's going to have to explain himself to Bob. Or, in contrast to that, if the miner on the other side of the network that had in their transaction data that coin going to Bob, if they happen to win the race, well, they can take that block of data with the transaction to Bob and the solution to that puzzle and broadcast it to the network. And everyone on the network will say, oh, yep, that solution is valid. They won. Okay, there you go. Let's move along to the next round. And then in contrast, well, Charlie's going to have to explain himself to Alice. Now, this competition happens on the Bitcoin network every 10 minutes. So a block is found and it goes and joins the chain. 10 minutes later, roughly, another block is found and it joins the chain as well. 10 minutes later, the same thing happens again. And all of these blocks of transaction data stack one right on top of the other sequentially. And they're chained together with cryptography, with mathematics, such that if someone tried to swap out one block and replace it with another, it would become very quickly apparent to everyone what they were trying to do, and that counterfeit version of the blockchain would be rejected. So who are these miners and why would they choose to do all this work? Well, like everyone else on the network, a miner is anyone in the world who chooses to buy that fancy computer and then connect it to the network. And they might do this due to economic incentives. Every time a block is mined or found, every time there's a solution found to that puzzle, the Bitcoin software rewards the miner that found that block or mined that block with new Bitcoin. Every time a Bitcoin block is found, that miner is given 6.25 new Bitcoin. So these miners are out doing this work due to economic incentives, right? And really this entire machine, this entire network runs off of what I like to call incentive engineering. And that's how you get this entire complicated yet entirely voluntary system to keep running and to stay secure and stay resistant to attack. It all runs off of incentive engineering. It's pretty cool stuff. So let's kind of recap what's actually happening here, or look at different ways to think about this. Again, what we're doing is we're coming to agreement on data with people we don't know and don't trust. And it's not just sharing data, because that's what happens on the internet all day, every day, but very specifically coming to agreement on data with people that we don't know and don't trust. Also, let's remember that cryptography does the job of validating transactions, of making sure someone actually owns that Bitcoin and has indeed signed that transaction, but it doesn't solve the problem of ordering those transactions. That's where we need the blockchain and this consensus algorithm. And so blockchains have very interesting time-stamping properties. And also, this whole system creates essentially digital scarcity. It creates this ledger where you can maintain a digital scarcity as a protocol without that centralized server or that business who's running things. Let's think for a moment about the architecture of this system, because it's very important when considering what applications will and won't work. Remember, we're agreeing on data with people we don't know and don't trust all around the world. And the architecture of this system is such that everyone has to know about everything. And number one, this has some big privacy implications. Now, there have been some coins that have been made, sort of privacy coins, which address these privacy concerns, but that basic architectural structure is still that everyone needs to know about everything. So because of this, I'm very cautious of any blockchain use cases that involve sharing private data, right? That could be a big concern. Also, this creates a big scaling problem, right? Everyone has to know about everything, so the more data you get on the system, the more and more difficult it gets to manage that. There are many scaling solutions in the works, but it's something to definitely keep in mind. Also, another thing to keep in mind here is this entire process is very resource intensive. As I always like to say, blockchains are not databases. They are incredibly slow, inefficient, and expensive databases, right? It takes a lot of resources, a lot of computers, a lot of electricity to keep this whole system running. And if you just need to share data, set up a WordPress website, right? You don't need a blockchain. Now, you might need a blockchain blockchain if you need some very specific blockchain features. For example, immutability. And that's just, immutability is just a fancy way to say uneditable. It means that there's no one that has admin rights to the Bitcoin blockchain. No one can go back and change any of that information. Essentially, information in a blockchain is written in stone, so to speak. You also get censorship resistance. Because it's an entirely decentralized network, there's no one entity that can change any of the data or manipulate any of the data or stop any of the data from being sent around. So you have a lot of censorship resistance built into these open blockchain systems. Now, all of this that I've just described was the state of affairs in 2009 when the Bitcoin network was launched. And since then, there have been thousands of blockchains created. And there have been all kinds of different consensus algorithms that have been created and many blockchains that are built for very, very specific use cases. But we'll cover all of that later. But now you've reached the end of the video. I hope you've learned something. Remember, watch this video as many times as you need to. Blockchain technology is new stuff. Sometimes it's difficult to really grasp what's going on because we don't really have a bucket to shove it into in our head. It's new and different stuff. So I recommend reading the Bitcoin white paper and watching this video as many times as you need to. And don't forget to check out the many other resources provided by Velas Commerce, and you can always reach us at velascommerce.com.